All right, guys. So I want to talk a little bit about something called L'Hopital's rule and indeterminate forms. So L'Hopital's rule is going to let us take the limit of all kinds of new things. And we briefly mentioned L'Hopital's rule way back when we were talking about taking limits. And we're going to see that some of our old ways of taking limits we can now replace using L'Hopital's rule. Not all of them, but some of them. So L'Hopital's rule basically says if we have the limit of a quotient, so notice that I have f of x over g of x, taking the limit as x approaches a of that quotient, okay, and we get something called an indeterminate form. There are many indeterminate forms. The two we're going to start focusing on is 0 over 0, or infinity over infinity. And here I'm not going to worry about positive and negative infinity, positive, negative infinity, either one. If I get 0 over 0, some version of infinity over some version of infinity, those are going to be known as indeterminate forms. And the truth is we don't know what happens here, okay? It depends on, in a sense, whether the top or the bottom goes to 0 faster, and over here whether the top or bottom goes to infinity faster. Just kind of a weird kind of quantification. But if we have either one of these indeterminate forms, assuming that the derivative exists at a, then we can take the limit as x approaches a of f of x over g of x and equate it, or say that it's equal to, the limit as x approaches a of the derivative of f over the derivative of g. Now notice this is not a quotient rule problem, okay? We're literally taking derivative of the top over derivative of the bottom. This is not giving us an overall derivative of the quotient of these two. All it's saying is this is a way to calculate the limit, okay? Now, L'Hopital's rule is really powerful because of this. So let's look at a couple of examples, okay? And they're both going to be examples that we could have solved using other techniques. So let's consider this. Okay, so let's say we're trying to take the limit as x approaches 4 of x squared minus 16 over x minus 4. Now, first thing we're going to do is make sure we have one of these indeterminate forms. So if I were to take 4 and plug it into this, I'd get 4 squared minus 16, which is 16 minus 16, which gives me 0, over 4 minus 4, which is 0. In other words, which is an indeterminate form. Okay, now, originally, our method for doing this was to factor and cancel. Because when I factor the top, x squared minus 16, which is the difference of perfect squares, into x plus 4 times x minus 4, and then cancel, I'm really taking the limit as x approaches 4 of the factor that's left, x plus 4, which I can solve with direct substitution. Plugging 4 in here gives me 4 plus 4, which is 8. Okay, so now let's do the same problem using L'Hopital's rule. So L'Hopital's rule says when I have a problem of an indeterminate form, 0 over 0, infinity over infinity, remember this is the 0 over 0 case, I can apply L'Hopital's rule. This is not formal notation, this is Megan notation. This says I'm taking LHR, L'Hopital's rule, which means I'm going to do the limit as x approaches 4. That doesn't change. And now I'm going to take the derivative of the top. The derivative of x squared minus 16 is 2x over the derivative of the bottom. The derivative of x minus 4 is just 1. And now notice I no longer have that indeterminate form. Now I have something that I can directly plug into, right? So I'm going to plug 4 in. 2 times 4 over 1. Oh, look at that. We got 8. The same answer we got using factor and cancel, which is good. Otherwise, we broke math. Okay. Let's look at another example where we can apply L'Hopital's rule. And again, this is an example that we have seen before, or a type of example that we've seen before. Okay. So let's look at the limit as x approaches infinity of 4x squared minus 5x over 1 minus 3x squared. Okay, so first things first, we certainly get an indeterminate form here. When I plug in infinity, the top is going to go to infinity. The bottom's actually going to go to negative infinity, but I've got that infinity over infinity thing happening. That's an indeterminate form. Okay, now you may or may not remember our technique for dealing with things like this. When I have infinity over infinity, I'm going to use the trick where I pick the largest exponent in the bottom, x squared, and I'm going to multiply top and bottom by 1 over x squared. Does this vaguely ring any bells? And that's going to change this problem to be limit as x approaches infinity. Notice I'm multiplying by 1 over x squared divided by 1 over x squared. So it's not really changing anything. Applying this 1 over x squared to each term, 4x squared times 1 over x squared. The x squareds cancel, leaving me with 4. Negative 5x times 1 over x squared, negative 5 over x squared. One of the x's cancel, leaving me with 5 over x. All over, same game on the bottom, 1 times 1 over x squared. Negative 3x squared times 1 over x squared, the x squareds cancel, and I'm just left with negative 3. Okay, now remember by our rules of limits, we can take a limit of each piece individually. The limit as x approaches infinity of 4 is 4. The limit as x approaches infinity of 5 over x, remember that goes to 0. The limit as x approaches infinity of 1 over x squared also goes to 0. The limit as x approaches infinity of negative 3 stays negative 3, so I'm left with 4 over negative 3. Okay, now let's do the same thing, but let's do it with L'Hopital's rule. So using L'Hopital's rule, we start out with the same limit. But now instead of playing this 1 over x game, I'm going to apply L'Hopital's rule. So I'm going to use my little shorthand, L'Hopital's rule. And L'Hopital's rule says, take the derivative of the top. The derivative of the top is 8x minus 5 over the derivative of the bottom. The derivative of the bottom is negative 6x. Now, notice that we actually still have an indeterminate form here. I have, when I plug in infinity, I have infinity over negative infinity. But L'Hopital's rule didn't work. Well, it did. We just sometimes have to apply it more than once. So we're going to apply L'Hopital's rule again, because I'm still in that indeterminate form, infinity over infinity. So again, L'Hopital's rule says take the derivative of the top. The derivative of the top is 8 over the derivative of the bottom, which is negative 6. Well, now when x goes to infinity, this just stays 8 divided by negative 6, which when I simplify is negative 4/3. The same thing we got using our old method. So now we can use L'Hopital's rule anytime we have things of the specific indeterminate form 0 over 0 or positive negative infinity over positive negative infinity. And L'Hopital's rule says if I have things of this form and only of this form, the limit is going to be equal to the limit of the derivative of the top, derivative of the numerator, which is very handy. Now, before I end this video and move on to another video, I want to just talk a little bit more about indeterminate forms. So we've talked about the indeterminate form that L'Hopital's rule directly applies to, and that's 0 over 0 or positive negative infinity over positive negative infinity. Okay, but there are other indeterminate forms. Okay, so an indeterminate form just means something that is indeterminate. We don't really know what it's going to come out to be. So another indeterminate form is when we have 0 times positive or negative infinity. Right? In general, we know that 0 times anything is 0. We also know that infinity times anything is infinity. So when these two come head to head, what happens? Who wins, 0 or infinity? And the answer is, it depends. It depends on who is kind of going to get there faster, which is a weird thing to say. But this is also an indeterminate form, the multiplication indeterminate form. We're going to see in the next video how we can take this indeterminate form and essentially turn it into one of these two indeterminate forms and then apply L'Hopital's rule. Similarly, other indeterminate forms include things like 1 to the infinity. Now, 1 to the infinity seems kind of straightforward, right? Isn't 1 to anything 1? Well, things get a little weird when we throw that infinity in. So 1 to the infinity is another indeterminate form. So is 0 to the 0. Because again, in general, we know that 0 to any power is 0, but anything to the 0 power is 1. So when I combine those two together, what do I get? That's another indeterminate form. And the third indeterminate form that we're going to talk about is infinity to the 0. And again, we run into the same type of problem that we did with these other two. Now, all three of these indeterminate forms are going to be treated sort of the same way. We're going to use something akin to logarithmic differentiation, where we use a natural log to get stuff out of the powers. So I'm going to record one more video that just talks about those. Okay? The big thing to remember is L'Hopital's rule only applies directly to things of this form, 0 over 0, infinity over infinity. We have other indeterminate forms, the multiplication form, 0 times infinity, or these exponential forms, 1 to the infinity, 0 to the 0, infinity to the 0. And it turns out we can take these and basically turn them into something that looks like this with a little algebraic manipulation, allowing us to then apply L'Hopital's rule.